Welcome back, everyone. Today's deep dive might sound a little intimidating at first, but I promise it's really fascinating stuff. We're going to be looking at coordination compounds.
And organometallic chemistry.
Yeah, from some university lecture notes. So pretty in-depth stuff, but
It's really cool. You'll see how it applies to like everyday things you wouldn't even imagine.
yeah, we'll find out why some metals are magnetic.
How we can tell what color a compound will be just by looking at its formula,
And we'll even get into catalysts.
like the ones used in hydrogenation.
So much cool stuff. To start off, though, let's just define what we're talking about here. What are coordination compounds?
Okay, so imagine a metal ion, like a tiny little metal center, surrounded by molecules or ions. We call those ligands. These ligands, they form bonds with the metal ion.
So like the metal ion is at the center of this little group.
Right, and that whole structure, the metal ion with its ligands, that's what we call a coordination compound.
Okay, that makes sense. I can picture that.
Mm-hmm.
But like, why do we care? Are these just something you learn about in a chemistry textbook? Or are they actually important?
Oh, they're super important, like way more than you'd think. For example, hemoglobin. You know, the protein in red blood cells that carries oxygen,
Yeah.
that's a coordination compound.
Wow. So we're literally talking about the chemistry of breathing right now.
Exactly. And that's just one example. They're also used in all kinds of industrial processes, like pigments, the things that give color to paints. Those are often coordination compounds. And catalysts, too.
Okay, so it's not just theoretical stuff. This is actually really practical.
Oh, yeah, absolutely.
You also mentioned we can figure out the color of a compound. How does that work?
So that's where crystal field theory comes in. It explains how those ligands, the molecules surrounding the metal ion, how they affect the energy levels of the electrons in the metal.
Okay, I kind of remember that from chemistry class. But it's been a while. Can you remind me how it works?
Sure, so you have these d orbitals, right? They're like different regions around the metal ion where electrons can be.
Right.
And when the ligands come in, they create an electric field. And that field, it interacts with the d orbitals, and it actually changes their energy levels.
So the ligands are messing with the energy of the electrons.
Yeah, basically. Like in an octahedral complex, that's where you have 6 ligands arranged kind of like at the corners of a cube around the metal.
Okay.
The electric field from the ligands, it splits those 5d orbitals into 2 groups. 2 of them go up in energy, and the other 3 go down in energy.
So there's this energy difference now between those two groups.
Right. And that energy difference, we call that the ligand-field splitting parameter, or AO for short. And that duo, that's what determines the color we see.
Okay, I see. So how does that determine the color?
So when light hits the compound, right, some of that light can be absorbed. The electrons in those lower energy d orbitals, they can absorb the energy from the light and jump up to the higher energy orbitals. And the specific wavelength of light that gets absorbed, that depends on AO, that
Yeah.
energy difference. So for example, let's take a compound called hexaquatitanium-3 ion, that's TiOH2 63 plus Wei.
Okay.
It's got this beautiful violet color, and that's because it absorbs green and yellow light. And what we see, the violet color, that's the leftover light, the wavelengths that weren't absorbed.
So the color we see is like the opposite of what the compound absorbs.
Yeah, you could say that. It's the complementary color.
Wow, that's really cool. So by understanding how different ligands affect that energy splitting, we can actually predict what color a compound will be.
Exactly.
You also mentioned that this theory, crystal field theory, it explains more than just color. What else can it tell us?
It can also tell us about the stability and the magnetic properties of coordination compounds.
Oh, interesting. So like how strong the bonds are between the metal ion and the ligands.
Right, and whether a complex is high spin or low spin, which determines its magnetic behavior.
High spin, low spin. I don't think I've heard those terms before. What do they mean?
So basically, electrons, they like to have their own space, right? So they would rather occupy different d orbitals by themselves than pair up in the same orbital.
Okay, yeah, that makes sense.
But sometimes that energy difference between the orbitals, that duo we were talking about,
Yeah.
if it's really large, then it becomes more favorable for the electrons to just pair up in the lower energy orbitals, even if it means sharing space.
So it's like they're deciding whether it's worth the energy to move to a different orbital or just bunk together.
Yeah, that's a good way to think about it. And that's where high spin and low spin come in. In high spin complexes, DO is small, so the electrons they're more likely to stay unpaired, even if it means occupying those higher energy orbitals.
And in a low spin.
In low spin complexes, dou is big, so the electrons are more likely to pair up in those lower energy orbitals.
Okay, I think I'm getting it. And so that difference in how the electrons are arranged, that affects the magnetic properties of the compound.
Exactly. Because unpaired electrons, they create a magnetic moment.
So the ligands in the metal, they're working together to determine how the electrons are arranged. And that affects not just the color, but also the magnetic behavior.
Yep, it's all connected.
This is so cool. I love how all these properties are linked together.
Me too. And we're just getting started with crystal field theory. There's still so much more to explore.
Yeah, like what?
Like how different types of ligands affect that energy splitting,
Yeah.
and how it all connects to the spectrochemical series.
The spectro what now? That sounds intriguing.
It is. Maybe we should let all this sink in for a bit, though.
Yeah, that's probably a good idea. My brain's already working overtime.
We'll come back and dig deeper into it after a short break.
Sounds good. We'll be back in a bit with more on the fascinating world of coordination compounds.
And ligand field theory.
Stay tuned.
Welcome back. So we were talking about crystal field theory before the break and how it explains things like color and magnetism in coordination compounds.
Yeah, it's amazing how those tiny little ligands can have such a big impact.
Right. But crystal field theory, it's actually a simplified model.
In what way?
Well, it treats those ligands like they're just point charges, just little points of electric charge.
Right.
But in reality, they're molecules or ions with their own electrons and orbitals.
Right, of course.
So ligand field theory, it takes that into account. It considers the actual overlap of those orbitals between the metal and the ligands.
So it's like we're getting a more detailed picture of what's going on.
Exactly. And when you look at it that way, you realize that the bonding between the metal and the ligands, it's not always just simple attraction. There can be different types of bonding going on, like pi bonding, for example.
Pi bonding. I remember that term, but can you refresh my memory?
Sure. So in pi bonding, you have overlap of orbitals that are kind of parallel to the bond axis, not head-on like in sigma bonding.
Okay, right.
And those pi bonds, they can either increase or decrease that energy splitting we were talking about.
Interesting. So the type of pi bonding affects that energy difference.
Yeah, exactly. Some ligands, we call them pi donors, they have electrons in their pi orbitals that they can donate to the metal.
Okay.
And that actually decreases all. It kind of shrinks that energy gap between the d orbitals.
So are there ligands that do the opposite, that increase its element?
Yeah, those are called pi acceptors. They have empty pi orbitals that can accept electrons from the metal.
Okay, so they pull those electrons away, and that makes the energy gap bigger.
Right. Good examples of pi acceptors are things like carbon monoxide and nitrogen.
And those are important in organometallic compounds, right?
Exactly. We'll get to those in a bit.
Cool. But before we move on, I'm curious about how stable these coordination compounds are. Are they like fixed structures, or can they change over time?
Oh, they can definitely change. One of the most common things that happens is ligand substitution. That's where one ligand gets replaced by another.
So those ligands can swap places.
Yeah, it's like a constant dance of molecules. And how easily a ligand can be substituted, that depends on a few things, like the ligand field stabilization energy or LFSE.
Right, we talked about that. It's that extra stability that comes from the splitting of the d orbitals.
Exactly. So the higher the LFSE, the less likely a ligand is to be substituted.
Makes sense. It's like a stronger bond, harder to break.
Right. And there's another factor called the chelate effect.
Chelate effect.
Yeah, chelating ligands are ligands that can bind to the metal through multiple points, like they have multiple arms to grab onto the metal ion.
Okay.
And those chelating ligands, they also tend to form more stable complexes.
So it's like they have a better grip on the metal ion.
Exactly.
So we've got ligand substitution. What other kinds of reactions can happen with these coordination compounds?
Well, there's a whole other category called redox reactions. That's where electrons get transferred between species.
Oh, right. Redox reactions, like oxidation and reduction.
Yeah. And those are super important in lots of chemical processes, even in our bodies.
Wow. So how do those redox reactions work in coordination compounds?
There are two main mechanisms, inner sphere and outer sphere.
Okay, what's the difference?
In inner sphere mechanisms, the electron transfer happens through a shared ligand. It's like the ligand acts as a bridge between the two metal centers.
So they're sharing an electron through that bridge.
Right. And in outer sphere mechanisms, the electron transfer happens without any direct contact between the coordination spheres. The electron kind of tunnels through space from one metal to the other.
Tunnels through space. That sounds kind of crazy.
Yeah, it is pretty wild. It's a quantum mechanics thing.
So in one case, they're directly connected, and in the other, they're not.
Yep. That's the main difference.
Wow, this is all so fascinating. We've covered so much ground already, from crystal field theory to ligand substitution to redox reactions.
I know, right? It's
Yeah,
amazing how interconnected everything is.
it is. And now I'm really excited to dive into those organometallic compounds and see how they fit into all of this.
Yeah, they're pretty special. They have their own set of rules and behaviors.
Like what?
Well, one of the key concepts is the 18-electron rule. It helps us predict the stability of organometallic compounds.
Another rule. What's so special about 18 electrons?
So just like atoms want to have a full outer shell of electrons to be stable,
Right.
organometallic compounds, they often try to get a total of 18 valence electrons around the metal center.
Hmm. So it's like a magic number for stability?
Yeah, you could say that. It's not always 18. Sometimes it can be 16, depending on the geometry and the ligands involved.
Okay, so there's some flexibility there.
Right. But understanding this 18-electron rule, it gives us a lot of insight into how organometallic compounds behave.
I'm starting to see why these are so interesting. They're like the rebels of the chemistry world.
Yeah, kind of. They definitely have their own unique character.
So what kinds of reactions can these organometallic compounds do?
Oh, lots of cool stuff like ligand dissociation, oxidative addition, and of course, hydrogenation catalysis.
Hydrogenation. That's the one with Wilkinson's catalyst, huh?
You got it. That's a
Yeah.
classic example of organometallic catalysis.
I can't wait to hear more about that, maybe after a short break. My brain needs a little time to process all this amazing information.
Sounds good to me. We'll be back in a bit to explore the wonders of organometallic reactions and catalysis.
All right, we're back and ready to dive into some of those really cool organometallic reactions,
Yeah.
especially that hydrogenation you were talking about.
Yeah, hydrogenation's a big one. It uses what's called Wilkinson's catalyst.
Okay, so before we get into that, can you just remind me what ligand dissociation is again?
Oh, sure. So basically, one of those ligands, the molecules attached to the metal ion,
Right.
one of them just breaks off. It leaves the metal center.
So there's like an empty spot now.
Exactly. And that's where the fun starts. Because then other molecules can come in and bond to the metal.
It's like opening up a space for something new to happen.
Right. And that's how you get all these really interesting transformations, like oxidative addition.
Oxidative addition, what's that?
So in oxidative addition, you have a molecule like hydrogen gas, for example, or maybe an alkyl halide,
Okay.
and it adds to the metal center. So now the metal is bonded to those new atoms, and its oxidation state goes up.
Oh, I see. So it's like the metal is grabbing onto those new atoms and making them part of its structure.
Exactly. And that's a key step in a lot of catalytic cycles, like in Wilkinson's catalyst, for example.
Okay, so let's talk about Wilkinson's catalyst. I remember you said it's used in hydrogenation, right?
Yeah. So hydrogenation, that's the process where you add hydrogen gas, H2, across a double bond.
Right, like turning an alkene into an alkene.
Exactly. And it's super important in a lot of different industries, like making margarine.
Really? Margarine?
Yeah. And all sorts of other things, pharmaceuticals, fine chemicals, lots of applications.
Wow, that's pretty amazing. So Wilkinson's catalyst makes that hydrogenation happen.
It makes it happen way faster, like thousands or even millions of times faster.
Wow. Okay, so how does it actually work? Like step by step.
Okay, so first you have that oxidative addition we were talking about. The hydrogen gas adds to the rhodium metal in the catalyst.
The rhodium. That's the metal in Wilkinson's catalyst.
Yeah. So now you have this rhodium complex with two hydrogens attached to it. Then the alkene, the molecule with the double bond,
Yeah.
that comes in and binds to the rhodium too.
So now the rhodium's holding on to both the hydrogens and the alkene.
Exactly. And now they're all close together so they can react.
This is getting good. What happens next?
So then one of those hydrogens that's attached to the rhodium, it moves over to one of the carbons in the alkene.
Okay.
And that forms a new carbon-hydrogen bond.
So now the carbon has an extra hydrogen.
Right. And then the other hydrogen on the rhodium does the same thing. It moves over to the other carbon in the alkene.
So now the double bond is gone, and we have an alkene.
You got it. And that alkane, it's no longer bound to the rhodium, so it just floats off.
So the catalyst is ready to do it all over again.
Exactly. That's why we call it a catalyst.
Yeah.
It speeds up the reaction, but it doesn't get consumed in the process.
Wow, that is so cool. It's like a tiny little machine just churning out alkanes.
Yeah, it's amazing what these organometallic compounds can do.
This whole deep dive has been incredible. I
Yeah.
feel like I've learned so much.
Me too. It's been fun exploring this stuff with you.
Yeah, thanks for guiding me through it all. I probably would have gotten lost without you.
No problem. Always happy to talk about chemistry.
So for everyone listening, if you're interested in learning more about this stuff, definitely check out those lecture notes we mentioned at the beginning.
Yeah, they're a great resource. And there are tons of other books and websites out there too.
And don't be intimidated by the fancy terms. It's really not that complicated once you break it down.
Yeah, it's just molecules dancing around.
Exactly. And that dance, it's happening all around us all the time. It's
What?
the chemistry of life.
Well said. Keep exploring and keep asking questions. That's what science is all about.
Couldn't agree more. Well, that's all the time we have for today's deep dive. Thanks again for joining us, and we'll see you next time for another adventure into the world of science.